Hi, my name's Andrew McLaren, and I'm going to help you understand the range formula, how you can make it, which is not something that is typically seen in like high school physics, but you will see it in college physics in class, but not normally on the exam. So the range formula is probably one of my least favorite formulas that I see at the beginning of the year because sometimes teachers just give this to students and they plug it in. And yes, you can do that, but it is a much harder thing to understand where this comes from. But I'm going to do my best to help you see where this comes from. If you needed to, you can even make this on the fly, but it requires quite a bit of background information with math as well as some physics stuff that's a little bit tricky. So if we're looking at something where you're hitting a ball or it's doing projectile motion and it starts at the ground and then it comes back down to the ground, your initial velocity up is the same as the velocity down. You will do some stuff with energy later on, showing that when you have the same potential energy, you have the same amount of kinetic energy if we're assuming there's no air resistance or friction or anything like that. So this velocity up should be equal to the velocity down. You can kind of see that in this equation here. When there's no change in x, the velocities should be equal to each other. So if we're talking about the y direction, if there's no change in that height, the final and the initial velocity should be equal but opposite. Like one's a positive number, one's a negative number. And you can do this with like some simple numbers to just kind of see the relationship there. I've worked through this problem already. This is a problem that I went over with a tutoring student. But the main idea here is that you're trying to relate the time that this thing is in the air equal to itself, but you're getting one equation for the x-axis and one for the y. So if we're thinking about the x-axis, there's no acceleration. You can kind of rearrange this formula knowing that Vx is the same as V initial times the cosine. You can kind of substitute that in for that. And in this problem, we do have the distance that it's gone off to the side. We do also have the y-axis, which can be thought of as the acceleration being the change in y over t. And as I was saying earlier, the velocity upward and downward, they're equal to each other, but one's going to be a negative number, one's going to be positive. So you can kind of see that I've got that with the negative out here for the v final and the v initial being a positive. So when you do the change in velocity, it's 2 times the initial velocity, but as a negative number. And we do have a negative acceleration as well, so you've got a negative canceling out with another negative here. So it works out to giving you a positive time with that positive velocity initially. We can also do a little substitution in here where we have, instead of Vy, we have V naught is equal to the sine times the angle. So we've got the that triangle being used to relate our sine and cosine functions to those different components. Now we have this time that's in the flight where this time is equal to itself. We can plug in these two equations and what's equivalent to each other. It's a bit tricky doing some rearrangement of this formula, so I was just showing with my student this is similar sorts of math relations and how you might simplify them just with like simple numbers. But if we look at the big picture, you're going to end up having these velocities and these cosines and sines times each other. And you should be able to kind of solve for v naught eventually at some time using this. So you've got v naught squared, which is equal to some number, which you could then square root and get that final velocity. Now, if you're trying to use the range formula, they're using sine 2 theta. So if we do trig function sine cosine, there's this relationship if you have sine 2 of something, if you have the sine and the cosine times each other, you can relate that to 2 times the initial angle right here, which is coming into play in this formula. So you can see that we had sine times cosine, and there was a 2 times in the number here, so there's like a 2 out front. So you can think about that as being 2 that we're talking about here. So you could rearrange this formula to have the sine times the 2 times of the angle, which kind of comes from the fact that there's 2 times that initial velocity with it going up and going down. So there is a little algebra trick that you can use to find the range formula very quickly and easily and summarize that into this equation that is very abstract and very weird. But if we do know the gravity constant, that initial velocity, and the angle, we should be able to relate that to how far it's gone. In the context of this problem, we knew how far it went. And so you could then go back and find the V naught. So like we could take this equation right here and think about plugging it in into the numbers that were provided. So like we had in the problem, we had the range in the x direction. We know what gravity is. And we also even know what this angle was. So you should be able to solve for what the V naught was, given that you've got everything else in that equation. I'm not going to go ahead and do that in this video, but if you'd like to challenge yourself, you can plug in the numbers and see what you get doing it that way. It's the same math. It's just giving you an equation to work with versus making you solve for it each time, which is my preferred method. But also I don't like using that formula, and you're not likely to see this even in a college physics class on an exam, unless you're like a physics major. They might do like one question related to this, but it's not the focus. There's a lot more easier relationships that show similar levels of understanding. This is just using some weird trig function tricks with this version of the formula. Okay, all right, that's everything that I wanted to go over. Thank you for joining me. Best of luck.